we discussed, I don't remember exactly, but last time, that the metric tensor changes on a sphere to something like this.
Yeah.
Geometrically. How was
That's
that
right.
obtained again?
Why this is the metric tensor?
Yes.
Because you always have to write it what it means, that. And it is coordinate dependent. So this is in theta phi coordinates for a sphere of radius 1.
Right.
So this is equal to d theta squared plus sine squared theta d phi squared. And this is just Pythagoras' theorem, if you
this
wish.
is just obtained from like the polar transformation.
That I would say that kind of. So if you have here circle like that, and this is infinitesimal, then you calculate. This is ds squared. What is that? It is this length squared plus this length squared. And when this is a small triangle, this is 90 degrees, you can still have Pythagoras. But you have this distance, if the radius is 1, this is just, you know how much this is?
So that is 1.
This is 1. This is d theta.
So, I mean, from the equation, you would guess that it's something like sine theta.
Yeah, no. If I draw a circle, so this is inside a circle like that, and this is radius 1. What is this length?
Oh, r theta.
Yes, if this d theta and this is 1, it is just d theta. So this length is d theta, and this length. You can also calculate that because now the circle is like that, and the radius of this, because this is theta, so that means that this length, if I draw a picture like that, so that is this one. So this is theta. Then what is this?
Oh, right, and this is the center. So then that's sine theta.
This is sine theta. So this length is sine theta, and now I go here by an angle, small angle d phi. So then this length, what is that now?
So then it's sine theta d phi.
Yeah, so if I just used Pythagoras, that is d theta squared plus sine squared theta d phi squared. So this is just Pythagoras' theorem on a sphere. And that is why this is the metric, because this you can also write as g mu nu dx mu dx nu. And then you can just read off the metric in coordinates theta and phi.
Right. Okay, I think I have it.
So you can describe a curved manifold with a metric. Right. And that's really how to calculate distances on a manifold, because they are different, because you cannot go out of it. In the real space, you could draw, say, the shortest line between the North Pole. You could take a shortcut. But you think of it as being on the manifold itself, and you cannot get out of it. So you cannot make this shortcut.
Right.
Just like when you're on the Earth. On the Earth, you cannot go through the Earth itself. But if you want to go from here, say, to New Zealand, you have to go around it. And then you have to take into account that this is the distance on a curved manifold.
Right, so we want to minimize the distance between 2 points.
the smallest distance between the 2 points is when you have a large circle between the two.
I want to know, is finding this or deriving this similar to our process for like deriving the relativistic Lagrangian, where we were finding the minimum axioms?
No, the principle is the same, but I would say it is different, and so I didn't really use that. I kind of wrote it down because what is kind of obvious what the distance has to be in this case, because here you have, you know what if you have 2 points, you can decompose them in this way. To prove that this is also the shortest distance, probably you can prove it. It is maybe a little complicated because you would have to consider changes in it.
Right. So
I would not.
The axiom where we made a slight change to
so you would need a formula for the action, and you would have to calculate the geodesics, and then you have to use a little bit more of the formalism.
So today, I guess I just want to ask, how does this apply to more, well, the sphere is still interesting, of course, but more interesting shapes, like, I don't know, an ellipsoid, or even ones that don't end, like a paraboloid, or something like those.
Oh yeah, but it becomes more complicated to calculate. So I would not calculate it. I would use my computer to do the algebra.
Oh yeah.
So the algebra becomes much more complicated. So this is what you can still work out on a blackboard, but soon with almost any geometry, it becomes complicated. The simplest geometry is the so-called Poincaré disk, and which is non-trivial. Poincaré disk. And then the metric is ds squared is equal to dx squared plus dy squared divided by y squared. This type of metric. And you can work it out what the shortest path is. So it is inside the circle, and the shortest, these are the geodesics. These are the shortest path between 2 points. There's a circle which is perpendicular to this. So this is perpendicular. So you draw a circle. So if they are very close, then it is very small. If they are further apart, it is something like that. And this you actually can work out. I have a homework problem for today. This week's homework problem for the class is exactly to study this metric.
Ah, I see. So I intuitively get that the geodesic is like the path that an object will follow if it's free falling through space. But more formally, how are we applying it? And other than just measuring how an object falls through space, how can we measure an object's effect on space itself, or how an object's mass curves space-time?
You measure, you don't, you calculate it, you don't measure, you know what it is, you know light, so if you have a star here, and you know that starlight bends around the sun, which you can see if you would have observed the solar eclipse. When there's a solar eclipse, when the moon, this is the moon, is in front of the sun, this is the last distance. So light gets bent, and that means that actually stars, which are really behind the sun, you actually can see because light goes around it. And that has been observed. So light follows the path of geodesics. And you can actually calculate this effect from solving at Einstein equations.
Right, okay.
So we are not there yet, but you can do that. And so you can solve some of, but these are already complicated calculations. You have to solve a set of coupled nonlinear partial differential equations to actually get this effect right. But it can be done. And this is probably the simplest kind of problem. And even for this, if you calculate geodesics, I would use Mathematica. I would not do it by hand. You can do it by hand, but that is, you have to solve equations, and there's some work to do it. Because although if you just look what the solution is, it is like that. So you have to determine, so this is a circle, and this is another circle, and it should intersect at an angle of 90 degrees. And then you have to get the geometry right.
It sounds hard to imagine.
You know how you can calculate, you know the equation of a circle here, you know the equation of this circle, and this should be 90 degrees, something like that. And then this circle has to fit in here. Or you could just draw first a circle, then you know that, or maybe I draw it like that, you know this is center. So you know that this is 90 degrees, this is 90 degrees. And then you can draw, so this is a circle, and now I want to draw the other circle. So this is the small circle, and the big circle goes, I have to look at what is the big circle. Okay, now I actually drew it in, I should have drawn it the other way, because the small one is on this side, and now it is on the wrong side. So the big circle has this as center. This is center of the big circle, and then it goes like this. Let me see. It doesn't come out very nicely. But this should be the center of the big circle. It is not a good picture. And you can calculate it. It is algebra. So you only have to solve some quadratic equations, and then you can actually find a solution to this problem.
I see.
But it is work. You have to work on it, say, for a couple of hours to actually get this right. So it is not something as simple.
Right. So I swear there was another piece of talk.
You had a little piece.
Right. It was right over there.
Okay.
So the approach I was thinking of taking when I tried proving that the geodesic of the sphere was just a great circle was, I guess, just getting like a general form and spherical coordinates for the great circle and then fitting that into the geodesic equation. But that never worked out for me. So what different approach should I have taken?
Yeah, last time we kind of proved it. And so we looked at last time we looked at parallel transport on a sphere, and we found a solution for that. And the geodesics is if a tangent vector is parallel transported. That gives a geodesic.
But I thought we only showed that it works for, say,
we proved it for the equator. But the equator is an arbitrary coordinate. So when I have a sphere, I can choose, so this is sphere, and I can choose the equator anywhere where I like.
Right, I was thinking that was way too cheap for me, so I...
No, the other way is complicated. Because then you have to express this great circle in terms of these coordinates. So that's much more complicated. So I will not do that, because you end up with, for that I also would use computer algebra. You end up with complicated, it is doable, but you end up with complicated equations. I would not even do them on the blackboard, because they are too complicated.
Right.
Although they are really trivial to do. There's nothing real complicated, but you have to do this coordinate transformation, and it gets ugly. Yeah. The equations won't be simple.
I suppose this is just a property because the sphere is rotationally symmetrical. So if we just have the one geodesic, we can, like, I guess, rotate it around and...
Yeah, we can choose our coordinates as we want. I choose the North Pole just perpendicular to this plane. So this is the North Pole, this is the South Pole, and that defines my coordinates. So you always have freedom to choose your coordinates. And that is used extensively in general relativity to simplify the equations. That is to choose the right coordinates. Because if you don't do that, many of the calculations will be really hopeless. So you have to really use that you can describe geometry in different coordinates. And I gave, did we discuss that? The simple example is in flat space. What is geodesic motion?
Just a straight line, right?
This is just ax plus, so y is ax plus b. That is the geodesic. But now you can write this down in polar coordinates. Then it gets already complicated. Y is equal to r sine theta and x is equal to r cosine theta. So the equation becomes r sine theta is a times r cosine theta plus b. So this is the equation in polar coordinates. And then you can write down the geodesic equation in polar coordinates. And in polar coordinates, it becomes non-trivial because in polar coordinates, g mu nu, what is it?
So it's what we had over here.
So that's r and theta. These are just two dimensions. So that means that ds squared is equal to dr squared plus r squared d theta squared. So this is the ds squared in polar coordinates, because...
right, so it's the same thing we saw for the sphere, but instead it's like we have the radius and then a little slight sector of the circle.
Yeah. So this is now dr. So this is this is r times d theta. And if you use again Pythagoras, this is dr squared plus r squared d theta squared. And that is what you have here. So this is the metric. So this is the metric. From the metric, you can calculate the Christoffel symbols. And from the Christoffel symbols, you can write down the geodesic equation. And then you have to put this into the geodesic equation. And then you find that this is a solution. But it is actually already complicated because what is said is geodesic equation. It is, for example, dr squared d lambda squared plus, there's some Christoffel symbol, something like, I just write down one term, times d r d lambda times d theta d lambda. And we have to parameterize. So this is actually not really the right form we want, because we want to choose a lambda. That means we want to parameterize this curve. So lambda runs along this line. You could
take lambda as, say, tan theta, so y over x.
You could do that, but maybe we want it to be something that goes linearly on this curve, so that lambda actually measures the length of this curve. And so lambda, and you start at 0. Maybe, I don't know, you can start it here, and this length is lambda. And then you can calculate it. If this is alpha, then this is theta, that is r. Then we know that this length, lambda, is equal to, so the sine of alpha is this length. Let me call this y. So y divided by lambda, that is equal to the sine of alpha. And we also know that the sine of theta is equal to y divided by r. So we can eliminate y. So lambda is equal to y, and y is r sine theta divided by sine alpha. So this would be an equation for lambda. So this would be our parameter lambda. And then you see how complicated it gets, because you have to work out all differentials, and you have to also invert this r and theta in terms of lambda. So it gets complicated. In my lecture notes, I actually worked this out. You can look it up. You can work it out. It is basically straightforward. But I use Mathematica to check all the differentials and the equations. So the first step is to calculate the Christoffel symbols. And we can do that if you want.
Calculating the Christoffel symbols doesn't take too long. I'm sure most of them are probably 0. Because